picture this. You are right in the middle of your workflow, like completely in the zone.
Oh, I know this feeling already.
Right. You go to download a simple PDF, or maybe you are uploading a single image file for a project. You click the button and nothing happens.
Just that little spinning wheel?
Exactly. The little loading circle spins, it stutters, and then it just stops. Your entire web browser just completely freezes up.
It is a feeling of absolute immediate dread.
It really is.
I mean, it's the kind of technical frustration that makes you want to throw your machine right out the window, primarily because, the system is failing at one of the most basic tasks we ask it to do.
So you force quit the browser. You fire up a completely different browser thinking, well, maybe it was just a localized glitch.
Yeah, naturally. Blame the app first.
Right. So you try the exact same download again. Same thing. A complete freeze.
The worst.
You end up having to log completely out of your session just to get your machine to wake up, only to hit that exact same brick wall, like 3 attempts later.
Just a total workflow killer.
But today, for this deep dive, you are in luck. Because we are hunting down exactly that kind of ghost in the machine.
I love a good tech mystery.
Same here. Our single source today is this fascinating tech mystery blog post from April 19, 2026, written by a user named Ang. And the title is Vanishing the Ghost Mount, Solving GNOME's File Picker Deadlock.
That is quite the title.
It sets the stage perfectly, right? So our mission today is to follow Ang's digital breadcrumb trail to uncover how a single forgotten line of code managed to create what they call a ghost mount.
A ghost mount, right.
Yeah, and we're going to look at how that ghost brought a completely modern GNOME 49 operating system to its knees.
Which is wild to think about. And, to validate what you're probably thinking while listening to this, while we are definitely getting into the weeds of Linux system architecture here, what we are really looking at is a masterclass in troubleshooting.
Absolutely. It's so methodical.
It really is. This isn't just about parsing one specific bug. I mean, it is a highly practical lens into understanding how the different layers of our operating systems communicate with each other, or more accurately, how they completely fail to communicate with each other when a single variable is out of place.
Yeah, it's a great lesson in that. So before we look at the exact code that broke Ang's system, we need to understand the symptom that kicked off this whole investigation.
Because the symptoms are so often misleading.
Exactly. It is a classic case of the symptoms masking the true disease. So Ang wrote in the post that this persistent bug in GNOME 49 had been plaguing them for, well, they said some moons.
Which is a great way to measure technical debt, honestly.
Right. But every single time they tried to repeatedly upload or download files, the browser just froze. It literally didn't matter if it was Firefox or Chrome. Total freeze.
And the natural assumption when your browser freezes while downloading a file is to just blame the browser itself.
Right, because that's what you're interacting with.
Yeah, the user interface locks up, the window goes gray, so your brain immediately concludes, okay, the application has crashed.
But here's where it gets really interesting. Ang had this major breakthrough. After some digging, they realized the browsers were completely innocent.
Oh, wow. Plot twist.
I know. They were totally taking the fall for something else entirely. The actual culprit was the GNOME 49 file picker itself, the underlying file manager program called Nautilus.
Okay, yeah. For those who might not dive into the backend processes often, Nautilus is what handles the graphical file management in the GNOME desktop environment.
The file explorer, essentially.
Exactly. So when you click upload in a web browser, the browser essentially hands the microphone over to Nautilus to pop open that secondary window where you actually select your file.
Right. And I was thinking about this, and it's kind of like thinking your car's engine is entirely broken because you can't leave your driveway, when really your garage door is just refusing to open.
Oh, that is a great way to put it.
Thanks. Yeah, you are sitting there revving the engine. The car's perfectly fine. It wants to go, but the exit path is completely blocked by a broken door. In this case, the browser is the car, and Nautilus is the broken garage door.
That analogy perfectly visualizes the dependency there. I mean, the car can't move until the door opens, so the car appears fundamentally broken to the driver.
Exactly.
But what's fascinating here is the specific bottleneck that Ang discovered blocking that door. They found a deadlock occurring between the XDG Desktop Portal and the dbus session bus.
Okay, let's unpack this for a second, because that's a lot of jargon.
It is, yeah.
Let's look at the mechanics of a deadlock in this specific context. So dbus is essentially the central nervous system of a Linux desktop.
Mm-hmm. Very central.
It's the core message bus that allows entirely separate applications to talk to each other and to talk to the operating system itself.
Right. And then the XDG Desktop Portal acts as the system's security bouncer.
Okay, the bouncer. I like that.
Yeah, because modern applications, especially web browsers, are increasingly isolated from the core system for security purposes. Like, they are sandboxed.
Which is good for keeping viruses out,
Yeah,
but makes things complicated.
exactly. The portal provides a heavily regulated, safe way for those isolated applications to request access to system resources.
So it's a controlled gateway.
Right. So if a browser wants to access your local files to upload something, it cannot just reach directly into your hard drive. It has to ask the portal to open a file picker.
So sticking with our metaphors, the browser asks the bouncer to open the file picker, and the bouncer sends that request as a message along the system's nervous system.
Precisely. But in Aang's case, those two critical components got trapped in a deadlock. They were both basically stuck waiting for the other one to provide a response, meaning neither could move forward at all.
Total stalemate.
Yeah, and the source post notes that this specific type of deadlock in GNOME is frequently triggered by two things, either mismatched portal backends or lingering mounts.
Lingering mounts, that's our suspect.
Yeah.
For those listening, a lingering mount is essentially a drive or a network location that the system thinks is there, but isn't quite functioning correctly.
Like a phantom limb for the computer.
Exactly. And that realization was the major pivot point for Aang. Knowing that Nautilus and the dbus session bus were just like staring at each other in a deadlock, the immediate question is, how do you force the system to show you what lingering mount is tripping everything up?
Right, because troubleshooting is entirely about isolating variables and verifying your assumptions. You have to actively ask the system what it currently believes to be true.
So Aang's next step was this standard, but really vital, diagnostic command. They opened the terminal and ran geomount L.
Ah, the trusty geo command.
Yep. That command queries the GNOME input/output system to basically list all the connected drives and volumes the system's currently aware of and managing.
It gives you a clear snapshot of the file system's current state, straight from the perspective of the desktop environment itself.
And Aang listed out the exact findings in the post just as they appeared on the screen. So drive 0 was an SSD, type gproxy drive. Drive 1 was another SSD, same type. Volume 0 was a 240 gigabyte encrypted drive.
Which all sounds completely standard.
Yeah, perfectly normal for their setup. But at the very bottom of the list was the anomaly. It said volume 1.tmp, and the type was listed as gproxy volume.
The TM volume.
Yeah.
I mean, that stands out immediately when you are looking at a list of standard physical drives and encrypted partitions.
Especially because, as Aang noted, this TM-BAV volume was listed in the terminal output, but it wasn't actually mounted in a usable way. It was a ghost.
Just hovering there.
Exactly. To test it, Aang went into the Nautilus interface and tried to manually mount it, just, clicking on it to see what the system would do. And I'd assume, since it's a broken ghost mount, the system just flat out refused to open it.
Oh, it did exactly that. GNOME threw a hard permissions error. Access denied.
Brutal.
It recognized the volume's existence, sure, but the current user completely lacked the authority to actually interact with it.
Okay, so Aang now knows this ghost mount is broken, but it didn't just manifest out of thin air, right?
No, computers only do what we tell them to do. Mostly.
Right. So to find the root cause, Aang went digging into the system's core configuration files, specifically the /etc/fstab file.
The file system table.
Yeah.
For context, the fstab file is essentially the foundational map of the system's storage architecture. Every single time your computer boots up, the operating system reads that specific file to know exactly what hard drives, what partitions, and what network drives it is supposed to automatically mount.
And where they belong in the directory tree.
Exactly. It's the blueprint.
Well, hidden in that foundational blueprint, Aang found the true origin of the ghost mount. It was a forgotten leftover line of code.
The classic leftover code.
Yep. Aang literally wrote that they had added it moons ago. The line read, TMP space, median TMP space, auto, X system D dot automount 03.
Okay, if we connect this to the bigger picture, that line tells a very, very familiar story for anyone who tinkers with their system's backend.
Oh, definitely.
Aang didn't add that line by accident. They added it in the past as a very specific band-aid. According to the post, it was a failed attempt to fix application permissions specifically for downloading files in apps installed via snap packages.
So it was just a legacy workaround.
Exactly.
Something they probably implemented late at night trying to solve a totally different problem, realized it didn't work the way they wanted, and then completely forgot to delete the instruction. We've all been there.
Oh, 100%. It highlights a really crucial lesson in system architecture and maintenance, though. Past technical band-aids almost inevitably become tomorrow's critical failures.
So true.
If you leave a broken or, experimental instruction in a core execution file like stab, eventually a system update, a new background service, or just a change in your daily workflow is going to trip over it.
Yeah, it's just a landmine waiting to go off.
Exactly.
Finding that bad configuration file is a massive victory for Aang. But reading through the post, it left me with a really significant question about the actual mechanics of the freeze.
Okay, what are you thinking?
Well, we know the FiStab line was bad and threw a permissions error, but Aang specifically points out that the total system freeze didn't happen on the very first try.
Right, it took a few attempts.
Yeah, it only happened sporadically, usually after the third or fourth attempt to download something.
And that delayed reaction is the real mystery at the heart of this bug.
Okay, let's unpack this. If the bind mount in that fstab file is broken, and it throws a permissions error the very moment you click on it, shouldn't the file picker just fail immediately every single time you click download?
Logically, you would think so.
Why is there this delayed fuse where it works for 3 tries, letting you think everything is totally fine, and then suddenly the whole system dies on the 4th?
That is the big question. And Aang's blog post actually breaks down the exact mechanics of this delay, and it perfectly illustrates a classic XDG Desktop Portal race condition.
Oh, a race condition.
Yeah, the sequence of events is fascinating because it shows how systems fail gracefully until they simply can't anymore. Let's walk through it step by step.
Awesome. Let's follow the data.
Okay, step 1. You click download in your browser, and the browser asks the portal to open the file picker.
Makes sense.
Step 2. A system component called GVFs, that's the GNOME virtual file system, immediately probes all the available mounts to see what storage options it should display to the user.
Right, to populate the menu.
Exactly. Naturally, it probes that Teampa bind mount that Aang left in the FStab file.
Yeah.
Step 3, that probe fails immediately because of the hard permissions error we discussed.
Okay, so it fails, but the browser doesn't freeze up at this exact moment.
No, it doesn't. And here is step 4, which is the crucial mechanical failure. Even though the GVF's probe failed, the XDG Desktop Portal keeps that specific communication request open on the dbus.
Wait, really?
Yeah, it doesn't instantly drop it and report a failure back to the browser. It just puts the request on hold, waiting for a timeout to occur.
But why? Why would it just hold a failed request open like that instead of closing it out and moving on?
Because the portal is designed to handle network drives and external devices that might be, slow to respond. It is built to be patient. It waits for the system to resolve the mount.
Oh, I see.
But because this is an auto-mount instruction with a permissions conflict, it enters a weird limbo state. The failure happens, but the portal still expects a resolution that is never, ever going to come.
Wow. So it's just hanging open in the background, consuming a tiny bit of resources.
Exactly. Now, step 5. As the user, you see the file picker stutter or fail, so you assume, oh, I misclicked, or it just glitched.
Right, so you try again.
Yep. You click download a second time, a third time, a fourth time. Every single time you click that button, you are generating a brand new request that hits that broken mount, fails, and gets put on permanent hold by the portal.
That is wild.
And these pending doomed requests begin to stack up silently in the background.
So you're just sitting there clicking the button, completely unaware that you're filling up a queue.
Which leads right to step 6. Eventually, that stack of pending requests hits the portal's strict internal limit for concurrent connections.
There's a limit.
Yes. We have to remember why dbus queues have these limits in the first place. They exist to prevent malicious applications or out-of-control scripts from flooding the message bus and causing massive system memory leaks.
Oh, so the limit is actually a safety feature.
It is, but in this case, the safety feature becomes the trap.
Right.
So step 7 is the final result, thread exhaustion. The queue is entirely full. The entire request thread locks up completely. No new messages can pass through the dbus regarding file operations.
It's frozen.
The whole system is now paralyzed, just waiting for that very first doomed request from your first click to finally reach its hard-coded timeout limit.
Okay, that sequence makes total sense now. It is exactly like a restaurant kitchen.
A kitchen. I like where this is going.
Think about it. Imagine a kitchen gets a ticket for an order that requires a very specific ingredient they don't have, let's say, a rare truffle.
Fancy recipe.
Very fancy. Instead of the chef looking at the ticket, realizing they are out of truffles, and canceling the order immediately to inform the customer, The chef just stands there at the pass.
Just staring blankly.
Yes, doing nothing, just staring at the ticket, waiting for a truffle to magically appear, because the restaurant protocol says, be patient with rare ingredients.
They are following the rules, but the rules don't account for an impossible situation.
Right. And while the chef is frozen there, the waiters keep bringing in more orders for the exact same truffle dish. Order 2, order 3, order 4.
Oh, no.
They slide them onto the ticket rail. The chef accepts the tickets, but is still frozen waiting on ticket number 1.
Right, because they have to be done in order.
Exactly. Eventually, the physical rail is entirely full. No more tickets can fit. The waiters can't place any new orders for any dish. The chef isn't cooking anything. And the entire restaurant grinds to a disastrous halt just because of a single missing ingredient on the very first ticket.
That is a perfect analogy. The restaurant hasn't burned down, the stoves still work, and all the ingredients for other meals are fully stocked, but the communication pipeline is entirely exhausted. Nothing can move forward.
Yeah, knowing exactly how that thread exhaustion happens on the D-bus, we can clearly see why Ang's previous attempts to force the system to work were completely futile, especially when you factor in how modern software packaging isolates applications.
Well, yeah, when you don't know the root cause of an issue, you naturally just try to treat the immediate symptom to get back to work.
Exactly. Ang detailed their old pre-discovery workaround in the post. Whenever the system froze up, Ang would open a terminal and run the command kill Nautilus.
A very common tactic.
Yeah, that forcefully executes the file picker process.
In our restaurant analogy, it's essentially terminating the chef and forcing the kitchen to hire a new one immediately.
Which, in theory, clears the board, drops the stuck tickets, and lets you start fresh. But here is the massive complication, and it's a fascinating technical detail from Ang's notes. This Kalal workaround only functioned for browsers that were installed via traditional DEB packages.
Interesting.
Right. For browsers that Ang had installed via Snap, running kill Nautilus did absolutely nothing. The freeze persisted as if the command had never been run.
Now, this raises an important question about how modern containerized package managers interact with deeply rooted system permissions compared to, traditional installation methods.
Traditional DEB installs place their files directly into the root file system, right?
Yeah.
So they're sharing the same permission space and namespace as Nautilus.
Exactly. So when Nautilus gets killed, the DEB browser immediately registers that the connection dropped. But Snap operates entirely differently.
Right, snaps are different.
Snap utilizes containerization namespaces. When you install a browser via Snap, it operates inside its own highly isolated sandbox. It is deliberately cut off from the wider host system to prevent malicious code from escaping the browser.
And Ang actually noted in the post that Snap applications are notoriously buggy when it comes to system permissions, specifically because of this rigid isolation.
Yeah, and the Kilo workaround failed precisely because of how Snaps enforce that isolation. The Snap browser is operating inside its container.
Yeah.
It doesn't communicate with the host's Nautilus process directly.
Oh, because it uses the bouncer.
Exactly. It communicates with the XDG portal, which acts as the bridge.
Okay, this makes so much sense now.
Right. When the deadlock happens on the D-bus, running a kill command on the host system terminates Nautilus, but it doesn't cleanly sever the connection bridge that the isolated Snap container is waiting on.
Browser's still standing there.
Yes. The container remains entirely trapped, waiting for a response from a portal queue that is completely jammed.
The container is so well isolated that it doesn't even know the process it's waiting for has been executed on the host system.
Which is pretty ironic.
Yeah. The Band-Aid doesn't stick because it's being applied to the wrong side of the sandbox, which led Ang to the inevitable conclusion. No more workarounds. It was time for the true cure.
Stop treating the symptoms and actually address the underlying configuration error.
The permanent solution was incredibly straightforward once the ghost mount was clearly identified. First, Ang went into that etc. stab file and deleted the problematic line entirely.
Just wiped it out.
Yep. But simply deleting a line in a configuration file doesn't instantly solve the problem. The system still has the ghost mount loaded in its active memory from the last boot cycle.
Right, because the system's current map still includes the ghost. You have to flush the current state to match the newly edited configuration file.
To do that, Ang had to run two specific commands in the terminal to forcefully unmount and obliterate the ghost directory. The first command was sudo mount L media nempa.
Now, the -L flag there is critical.
What does that do?
It stands for a lazy unmount. When a mount is caught in a D-bus deadlock, a standard unmount command will often just hang because the bus is locked.
Oh, because it's asking nicely and waiting for permission.
Exactly. A lazy unmount tells the system to immediately detach the file system from the directory hierarchy right now, and then clean up all the actual background references later whenever it is no longer busy. It forcefully breaks the link without waiting for permission.
I love that. Do it now, clean up later.
It's very effective.
Well, that was followed by the killing blow. The second command,
Mm.
sudo rm-rf median temp. Remove recursively and forcefully.
Yeah, that command completely deletes the physical directory folder itself from the drive. It ensures nothing can attempt to mount to that specific path again.
No more folder, no more legacy mount instruction in the ridstab, no more ghost.
A clean slate.
Yep. The problem was completely solved and the file picker deadlock vanished.
You know, it is incredibly satisfying to see a clean resolution like that.
It really is.
You strip away layers of misdirection, like the frozen browsers, the containerization quirks, you isolate the variables, find the root cause, and the permanent fix is simply deleting a legacy mistake and clearing the cache.
To bring it all back around for you listening, we started this journey with a seemingly random, infuriating web browser freeze that looked like a simple software crash.
And it was anything but simple.
Right. By following Ang's brilliant troubleshooting logic, we tunneled down through the GNOME 49 Nautilus file picker, identified a communication deadlock on the dbus session bus.
We watched an XDG Desktop Portal suffer from total thread exhaustion due to its own safety limits.
And finally landed on a single forgotten line in an XDAB file. And that line was originally meant to fix a rigid permission issue in a Snap application.
It is a perfect, almost poetic example of exactly how interconnected and honestly how fragile modern system architectures can be.
Truly.
It acts like a house of cards. Leave one broken legacy card in the deck, and eventually a totally unrelated process will pull it, bringing the whole structure down.
Yeah, everything is connected.
But, you know, thinking about Ng's journey leaves me pondering a really significant paradox regarding how we build these systems today. Yeah. Think about it. The author originally created that ghost map because they were trying to manually fix file downloading permissions for Snap applications.
Right?
And later, their terminal workaround failed specifically because those same Snap browsers handle system permissions so rigidly.
Wow, it really is a fascinating paradox. We build these complex sandboxes to keep our applications isolated and our host systems safe from vulnerabilities.
Exactly. Containerized app systems like Snap are designed from the ground up to enforce stability by locking down what an application can and cannot touch.
But looking at the sheer frustration this caused, we really have to ask,
Yeah.
are these notoriously rigid security sandboxes actually forcing users to implement dangerous system-level hacks like manually editing core stab files just to get basic functionalities to work?
It's a great question.
Are we designing security protocols that ultimately cause the exact catastrophic system failures they were built to prevent?
When the cure requires breaking the foundational map just to download a simple file, we really have to evaluate the architecture of the sandbox itself.
That is definitely something to chew on the next time your system tells you access denied while you're just trying to get your work done.
Definitely.
Well, for now, we're wrapping up this deep dive. Thank you for joining us on this digital ghost hunt.
It is a fun one.
And remember, the next time your machine freezes up entirely and you are ready to throw it out the window, sometimes the ghost haunting your machine isn't a massive system failure. Sometimes it's just a typo you made 3 moons ago. Catch you next time.